Hi, everybody. It's Professor Mitchell continuing with Chapter 2. Today, we're looking at Section 2.7 on further problem solving. In this section, we will solve problems involving distance, solve problems involving money, and solve problems involving interest. So you might be excited to hear that this is the last section we'll do for a little while on SLOD, which is solving application problems, in this case, again, using linear methods. Okay, so no more word problems for a little while. All right, so we'll start with some distance problems. This is a personal favorite of mine. The Jones family drove to Disneyland at 50 miles per hour and returned on the same route at 40 miles per hour. We want to find the distance to Disneyland if the total driving time was 7.2 hours. And I found this fun little meme. When I say, let's go to Disneyland, we go to Disneyland. All right, don't mess with her. Okay, so I'm going to switch over to the tablet. All right, so here's that problem. And I'm going to show you how we set these up. So remember a few sections ago, we talked about the formula distance equals rate times time. And the reason I'm writing it like that is because I'm going to make that into a chart. Okay, so typically, these distance problems will have, or the trip involved will sort of have two parts to it. And I'm not going to lie to you, these problems do take practice. I know they're challenging. Just hang in there, you'll get it. All right, so in this case, the two parts of the trip are the trip to Disneyland and then the trip home from Disneyland. Okay, so let's fill in what we know so far, and then when we get stuck, we will define a variable. So I think I know everything there is to know about the rates. They drove to Disneyland at 50 miles per hour. They drove home from Disneyland at 40 miles per hour. At this point, I get a little stuck, all right? Because they tell me that the total time for the whole round trip is 7.2 hours. So sometimes students will tell me when we do this problem in class, oh, well, then that means the trip there and the trip back both took 3.6 hours, right? Half of 7.2. But do you see the problem with that? The problem with that is that if they were driving different rates, specifically if they drove faster to Disneyland, then they didn't spend as much time driving to Disneyland, right? Because they got there faster. So at this point, we need to define a variable. So I am going to define my variable as t. And T is going to stand for the time to get to Disneyland. Okay, so I'll put a T here. All right, now my next question is going to be, then what is the time to get home from Disneyland? This is a kind of tricky question, and I will admit that we haven't done many problems where this kind of thing comes up because I've been saving them for chapter 4, but I couldn't resist doing this problem. Like I said, it's one of my favorites. So think back a few sections. I think it was 2.4 where we talked about the string problem. I got very excited about the string problem. And okay, so let's say to Disney from Disney. I'm just going to put some examples here. Sorry, I usually have pretty decent handwriting, but I'm squeezing it into a small space, so it's not that great. All right, so as we said, if it took them 3.6 hours to get to Disney, it would take 3.6 to get home. If it took them 3 hours to get there, it would take 4.2 to get home, right? These numbers have to add up to 7.2. If it took them 2.81 hours to get to Disney, I'm making this difficult for myself, then I believe it would take them 4.39 hours to get home. So now I'm going to ask you, well, what if it takes T hours to get to Disney? How did I get all of these numbers, especially these two, from these ones over here? Well, I got them by subtracting from 7.2. So if it takes 3.6 to get to Disney, it takes 7.2 minus 3.6 to get home. If it takes 3 hours to get to Disney, it takes 7.2 minus 3 hours to get home. If it takes 2.1 hours to get to Disney, it takes 7.2 minus 2.81 to get home. And if it takes T hours to get to Disney, it takes 7.2 minus T to get home. Okay. So that's what I'm going to fill in here. And I believe that's probably the hardest part of the whole problem, is just coming up with that. Okay. Now, just like in the last section, whenever you have sort of a formula written across the top, in this case, D equals R times T, those symbols, the equal sign and the multiplication sign, they carry down throughout the chart. Okay. So if it was 50 miles an hour getting to Disney and they drove for T hours, then that means the distance to Disney is 50 T. And if it took 7.2 minus T hours to get home, driving 40 miles an hour, then the distance home is 40 times 7.2 minus T. Okay. All right, so now we have to come up with an equation that will allow us to solve for T. So look this over for just a minute. Pause the video if you want to think about it. I definitely encourage that. So what's going to give us our equation, I'll give you a hint. They drove to Disneyland and returned home on the same route. That's your hint for how to come up with this equation. So you look at the distance to Disneyland, you look at the distance home from Disneyland, those two distances, they're equal, right? That's going to be our equation. These two distances are equal. All right, so that's going to be our equation. I'm going to write it on the next page. 50T equals 40 times 7.2 minus T. I'll distribute the 40. 40 times 7.2 is 28.8. No, it's not, is it? Yes, it is. Yeah, 28.8. Forty times minus T is minus 40T. Okay, so now I want to get the T's on the same side. So I'll add 40T to both sides. And that's going to give me 90T equals 28.8. Excuse me. And now I will divide both sides by 90. And it turns out that T is 28.8 divided by 90, which I'm doing on the calculator. And that comes out to Oops, I made a mistake. I knew that looked weird. Oh my gosh, how embarrassing. 40 times 7.2 is not 28.8, it's 288. Oh gosh. Okay. I could edit that out of the video and pretend it never happened, but I want you to know it's okay to make mistakes as long as you catch them. You might not have caught this particular mistake until later. I've done this problem a million times before, so I have the advantage of knowing what looks familiar and what doesn't. And also, I got a weird value of t when I went to do that. Okay, so 288 divided by 90 is actually 3.2. Okay. All right, so now I'm ready to write my complete sentence that represents my answer. I'm going to go back to the original problem because, and I don't think this has ever happened before in any of the examples, we need to make sure we answer the question that was asked. The question that was asked was to find the distance to Disneyland. It was not to find the amount of time it takes to get to Disneyland. All right, so we have one more thing left to do. So notice the distance to Disneyland is 50t. Okay, so what I need to do is take this 3.2, which again is the hours to Disney. The distance to Disney is 50t, which is 50 times 3.2, which comes out to 160 miles. And that's the answer we're looking for. Okay. As a check, you know what? I'm just going to go ahead and do this. Let's check to make sure that when we plug that value of t, 3.2, into this other expression for the distance, it should come out to be the same. And I can already see it does. 40 times 7.2 minus 3.2 is 40 times 4, which is also 160. Woohoo! Okay. So as I said, I've done this problem many times, and after a while, I started to get a little obsessed with it. And my obsession specifically was, where does the Jones family live? If they live 160 miles from Disneyland. So imagine that they live 160 miles north of Disneyland, and use your knowledge of the great state of California to make a guess where the Jones family lives. Do you think they live in Merced? Do you think they live in Fresno? Okay. I've asked this question to many classes, and I will usually have people guess Fresno, Bakersfield. Well, it turns out Bakersfield is a very good guess. The best answer I've ever been able to come up with is McFarland. All right, they made a movie about McFarland. It's about, what, a half an hour north of Bakersfield. So you can see from my old MapQuest map here that it is, what does it say, 161.62 miles from Disneyland to McFarland, I guess, depending on what part of McFarland you're in. All right, I have never gotten so obsessed that I've looked for a specific address that would come out to exactly 160, but anyway, okay. All right. Next problem. Oh no, suppose two trains leave a station at the same time. That statement, that, what's the word I'm looking for? That phrase makes a lot of people twitch. All right, that train left the station a long time ago. Okay, but two trains leave a station at the same time, traveling in opposite directions. One travels 8 miles per hour faster than the other. In 1.5 hours, the trains are 162 miles apart, and they want us to find the speed of each train. All right, so going back to the tablet. All right, here we go. So again, this is a distance problem. So we're going to use the formula distance equals rate times time. All right, and this time the two parts of the trip are the slow train and the fast train. Okay. Both trains travel for 1.5 hours. So this time we know everything there is to know about time. But I don't know the specific rates of the trains. All I know is that one train travels 8 miles an hour faster than the other train. So I think the thing to do in this problem is to let R be the rate of the slow train. This problem is easier, I think, than the last one. Okay, so I'm going to put R here, and then what would the rate of the fast train be? Since it travels 8 miles per hour faster, that means its rate is R plus 8. So the distance traveled by the slow train is 1.5 R. Distance traveled by the fast train is 1.5 times R plus 8. Okay. So now I'm ready to write my equation. The trains are 162 miles apart, which means the total distance traveled by both trains is 162 miles. And that is going to be my equation. All right, so here's our equation. I'm going to distribute the 1.5, which is going to give me 1.5 R plus 1.5 R plus 1.5 times 8, which is 12, equals 162. Combining these like terms, 1.5 R plus 1.5 R is 3 R. And why don't we take a little shortcut here? Subtracting 12 from both sides, I get 3R equals 150, which means R equals 50. All right, so now let's just make sure we answer their question. The question was find the speed of each train. So we know that one of them is 50. That's the slow train, which means the speed of the fast train is 58, right? So you can say something like the speeds of the trains are 50 miles an hour and 58 miles an hour. All right, let's see what's next. All right, that brings us to so-called money problems. Oh, good, let's talk about money. All right, so this is an example of a money problem. A bank teller is counting $20 and $50 bills. If there are 6 times as many $20 bills as $50 bills, and the total amount of money is $3,910, find the number of each denomination, which means the number of 20s and the number of 50s. So this is what the setup for this problem looks like. Again, I'm going to make a chart. It's a nice, way to keep the information very nicely organized. So I've got all this on the tablet. Let's go over there. Okay. So I think I need to jump right into defining my variables. So look here where it says there are 6 times as many 20s as 50s. So do you think it would make more sense to let X equal the number of 20s or the number of 50s? Well, technically you could do either, but I think it makes a little bit more sense to make X stand for the number of 50s. So X is going to go here. So if I have X number of bills and each one is worth $50, then that means the total value of those bills is 50X. And if I have X number of $50 bills and I have 6 times that many $20 bills, then I can write the number of $20 bills as 6X, right? And the value of those bills will be 20 times 6X. The total value of the bills is $3,910. And that comes from adding up the value of the 50s and the value of the 20s. So our equation is going to look like this. All right, so going to the next page, we have 20 times 6X plus 50X equals 3,910. This should be a nice, easy equation to solve. 20 times 6 is 120. So we have 120X plus 50X equals 3,910. 120 plus 50 is 170. 170X equals 3,910. And finally, dividing both sides by 170. I get X equals 3,910 divided by 170, which is 23. So again, let's just make sure we answer their question. The question was find the number of each denomination. We have found X, which is the number of $50 bills. So there are 23 $50 bills. And 6 times that many $20 bills, right? 6 times 23 is 138. This one's very easy to check. Just do 23 times 50. Which is 1,150. And then do 138 times 20, which is 2,760. You add those together, you get 3,910. Woohoo! All right. So the next one is one that I would definitely like you to try because it's very, very similar. And that's this one here. A collection of dimes and quarters is retrieved from a soft drink machine. There are 5 times as many dimes as quarters, and the total value of the coins is $27.75. They want us to find the number of dimes and the number of quarters. Exactly like the last problem. So please pause the video and try that one. I don't think you even need me to show you the chart for this one because the setup is going to be exactly the same. So please try this problem, do everything you can, and then come back and we will compare notes. All right, here we go. So like I said, the setup is exactly like the last problem we did. This time there are 5 times as many dimes as quarters. So it makes sense to let X equal the number of quarters. All right, so I'm going to put X here, which means the value of the coins is 0.25X. And if there are X quarters and 5 times as many dimes, that means there are 5X dimes. Total value of the dimes is 0.1 times 5X. And the total value of all the coins is $27.75. So we have our equation. 0.10 times 5X plus 0.25X equals 27.75. All right, 0.1 times 5X is 0.5X plus 0.25X equals 27.75. Combining the like terms, we have 0.75X equals 27.75. And then we will divide both sides by 0.75. All right, so using the calculator, we end up with 27.75 divided by 0.75, which comes out to 37. All right, remember that's the number of quarters. So there are 37 quarters and 5 times as many dimes, which is 185. And that one would also be very easy to check, right? Just check the total value of the quarters, the total value of the dimes. Make sure they add up to 27.75. All right, I believe that brings us to our last example. You're not going to see too many of these in the homework because I'm saving most of them for chapter 4. But this is one we can do now. Bruce Blossoms, so that's kind of a fun thing about your textbook author. She loves to put the names of people she knows in the word problems. All right, so this is probably a neighbor or somebody she works with. Anyway, Bruce invested a sum of money at 10% annual simple interest and invested twice that amount at 12% annual simple interest. If the total yearly income from both investments was $2,890, how much was invested at each rate? Switching over to the tablet one last time. So remember back in in section 2.5, we saw a formula. I don't remember if we ever actually used it, but that formula said interest equals principal times rate times time. Okay, so principal stands for the amount of money put in the account. R is the interest rate, written as a decimal. T stands for time, and then I stands for interest. All right, so Bruce divided his money between 2 accounts. We have the 10% account and the 12% account. So right under R, I'm going to put 0.10 and 0.12. For T, it says the total yearly income was $2,890. So that's just from 1 year. So we're going to put a 1 in both of the T spots. And now I'm ready to define my variable. I guess I'm going to have to do it up here because I didn't leave any room. He invested some money at 10% interest and twice that amount at 12% interest. So it makes the most sense to let X equal the amount invested at 10%. So that goes here. And then if he invested twice that much money at 12%, that means this is going to be 2X. So again, carry down your symbols. And that will help us figure out how to fill in the interest boxes. So the interest earned from the 10% account would be X times 0.1 times 1, which is 0.1X. And in the other account is 2X times 0.12, which is 0.24X. And those two amounts have to add up to $2,890. So you see my equation right here. Go ahead and solve that. That's an easy one to solve. 0.10x plus 0.24x equals 2,890. Combining those like terms, we get 0.34x equals 2,890. And now we will divide both sides by 0.34, which is going to tell me that X is 8,500. All right, so one last time, let me make sure I answer their question. How much was invested at each rate? So I need to put both. X was the amount invested at 10%. All right, at this point, we'll say this is close enough to a complete sentence. $8,500 at 10%, and twice that amount, which would be 17,000 at 12%. This one is also very easy to check. Just figure out what is 10% of 8,500, it's 850. And then 12% of 17,000 is 2,040. Those two amounts do add up to $2,890. Woohoo! All right. That's going to do it for section 2.7, and that's going to do it for word problems for a little while. We will see some word problems come up again in chapter 4, maybe a few easy ones in chapter 3. But in the meantime, we will take a little break from word problems. Have a great day, and we'll see you next time.